Word. All right. Yeah, so I wanted to dive back into linear transformation stuff more today. One reason I gave you the reprieve on the problem sets was because we sort of caught up to where we were, and I wanted to do more of this before I had you do homework on it. And I thought we might work together through one of these examples, and then I can say some general things about linear transformations. And then you can go back into groups and do some of these other problems. I'll specify specific ones that I want you to do. So we'll do that, and then we can come back together at the end and wrap up some stuff. So I think that's the plan for today. So let's just look at this number 3, this example, just to go through, remind ourselves all the terminology and stuff. It's been 5 days since I saw you, and you might want a little refresher. So let's dive back into linear transformations. And look at this example, which is number 3 from the handout. And it's t of x1 comma x2 is, what is that, x1 plus x2, 2x1 minus x2, and is it just 3x2. And so that's your output y1, y2, y3, right? So basically just saying, if I tried t of, maybe it's worth doing, if I did t of 7, 4 or something, that would just mean 7 plus 4, 2 times 7 minus 4, and 3 times 4, right? Which is, I guess, 11, 10, and 12. That was not intentional. Nice. I think maybe that works. So this is an input right here. If you input 7, 4, that vector, then your output is this vector, right? And so this is a transformation t from R2 to R3, right? The inputs are 2-dimensional and the outputs are 3-dimensional. And we could give it by a 3D matrix, 3 by 2 matrix, because you could rewrite this. We could write t of x1 comma x2. We could write that as the matrix columns 1, 2, 0, 1 minus 1, 3. Is that a way you guys kind of agree with that? Matrix times vector. I do the dot thing, that I get the same thing there. I also think it's nice sometimes to write this as the linear combination of the columns. All right, that's another way we could write it. x1 times the column vector 1, 2, 0, plus x2 times the column vector 1, negative 1, 3. And that's our y1, y2, y3. And so this is called the matrix of the linear transformation right here. This is we write t of x equals a times x. And that's our A. And A is called the matrix. The matrix of the linear transformation. The matrix of T. And in fact, you can kind of go back and forth between matrices and linear transformations. Like any linear transformation, you can write down a matrix. Any matrix, you can write down a linear transformation. So there's a sort of duality between those two. Make sense? Okay. So then the first question you might really ask is what is the image of T, right? So it's what are the all possible outputs? Because they land in R3, but I claim they're not going to be all of R3. Yeah, so what is the image? Remember, this is like a synonym for range. So we're fancy mathematicians now, and we use the word image. I.e., exactly which y1, y2s, y3s can we get? For example, 11, 10, 12 is in the image of T. Sometimes people write actually like I am T, like for the image of T. Right, 11, 10, 12, because we saw that as an output. Notation for the image. Okay. You see what I'm saying? Like that's in the image because we can actually get it explicitly as an output. There's an input that gives it as an output. Yeah, and then there's this question sort of in general, which outputs can we get? And the way we do that is well, you could also think about it as, there's a couple different ways to think about it. You can also think of it as the span of the columns, because every output is a linear combination of the columns. So it turns out that, notice from here, that the image of T equals the span of the columns of T. And there's a name for this. This is called the column space, or span of the columns of A, I should really say. I should refer to the matrix, span of the columns of A. And there's a name for this. This is called the column space. I'll talk about subspaces at some point. This is called the column space of A, just the span of the columns of A. So the image of T and the column space of A are really the same thing. And I'll say this kind of stuff over and over again, but like I mentioned, there's these different perspectives, right? There's like this row perspective of systems of linear equations. There's this column perspective of linear combinations of columns. There's this transformation perspective we're looking at now. And certain things in certain perspectives are equivalent to certain things in other perspectives. And so this is in the transformation perspective, and this is in the column perspective. Okay. But in particular, if we wanted to find it, we could just augment with the generic column and solve, right? So we do 1, 2, 0, 1, negative 1, 3, and then augment y1, y2, y3. And if we solve this, so I'm gonna have to do this by hand, kind of, right? Wait, is there, oh yeah, 1, 1, 2, okay. Yeah, so the thing is, how many pivots are you gonna have at most? 2, right? And so there's gonna be a 0 row. So you can kind of immediately say the image is not all of R3, because there's gonna be combinations of this that give you an inconsistent system. So maybe before I even row reduce, I can just say, at most 2 pivots. So the image of T is not all of R3. And it also should make sense, like we're kind of mapping 2-dimensional space into 3-dimensional space. You can't fill up all of 3-dimensional space with like 2-dimensional space. And you can even say here that there's going to be exactly 2 pivots, because why? Why is it fairly obvious there's exactly 2 pivots? The 2 columns, and what's specific about the columns? Like sometimes you could have 1 pivot, right? Yeah, Daniel. They're not scalar multiples of each other, exactly. Right, these aren't scalar multiples of each other, so you're gonna actually get exactly 2 pivots. In fact, exactly 2 pivots since the columns are linearly independent, sort of clearly, since the 2 vectors, the 2 column vectors are linearly independent. So in fact, that means that the image will be a plane. This image will be the span of the columns, will be a plane in R2. So image equals the span of the columns. It's a two-dimensional span, so it's a plane in R3. So I could give all the sort of qualitative analysis without doing anything else. I mean, it's easy with just two columns because you can just tell if they're scalar multiples or not. It's three columns, you usually have to do more to figure out, like, are they actually independent? You know. But if I wanted, I think I say in the problem, like, identify it as specifically as you can. Like in part B up there, what is the image of T? Is it all of R3 or something smaller? We just said it's something smaller. Identify it as specifically as you can. Well, we said it's a plane, but you can actually get the equation of the plane, right? If we row reduce this, oh, help me, Lord help me if I'm gonna row reduce by hand. I subtract twice the first row from the second. Just doing this because it's fairly quick. Is that right? And then I could just add the second row to the third now at this point. Is that right? I think some people got to this when we're doing it on the board also, but I'm not even writing down the row reduction steps. I'm just sort of like being kind of lazy about this. So 0 minus 3, y2 minus 2y1, 0, 3. And if I add them, I get minus 2y1 plus y2 plus, oh, that's a 0, plus y3. So in fact, that is what has to equal 0, that expression on the bottom. So we need minus 2y1 plus y2 plus y3 to equal 0, or we could say y2 plus y3 equals 2y1. But either way, this is a plane, right? And this agrees that this is a plane in three-dimensional space. It's a linear equation in 3 variables. By the way, what the example that we have up there, 11, 10, 12. Does it work? 10 plus 12 equals 2 times 11. That's a good feeling. Okay, so that's kind of, so this would be, if I wanted to specify it like the image as explicitly as possible, we could say something like that. Right, because it's actually something I'm going to talk about more and more, but maybe I'll just say it now just because it comes up a lot. But like, it's like I want to know if a vector is in the span of the columns or not, or if a vector is in the image or not. We could just think of the image as the all linear combinations of these two columns, right? So that's how you would generate the entire image, just take all linear combinations of this. So I could just generate, like I generated 10, 11, 10, 12 by just picking a specific x1 and x2. So just every choice of x1, x2 I could generate. I could just throw elements of the image at you over and over again. And I could, so sometimes I would call that like a vector generator. But if I give you a specific vector, I want to ask you if it's in the image. It's better to have an equation like this, because then you can just plug in the numbers and check, right? And so sometimes I call this like a vector tester. No one else uses this terminology. I kind of use it like, I think of this as a vector tester to test if it's in the image. A vector generator would be like the set of linear combinations. Because like you can basically define this image in different ways, right? So I guess what I'm saying is like, you could define, so the image of T equals, I could say the set of all x1 times 1, 2, 0 plus x2 times 1, negative 1, 3, sort of ranging over all x1s and x2s all real numbers, x1 and x2. Or I could say it's the set of y1, y2, y3 in R3 satisfying y2 plus y3 equals 2y1. Right, so those are two completely different descriptions, but they turn out to represent exactly the same points in space. Does that make sense? So maybe I'll just write this down. This is what I would call a vector generator, because you can just pick numbers for and this is what I would call a vector tester, because you can test any candidate. It's kind of nice to be able to have both descriptions of a set, right? Like I can generate elements as far as I can see, but I can also test elements to see if they're in there. Test vectors, okay. Any questions about that? Yeah.
Would that be the plane that?
Exactly. This is exactly the plane. This is the equation of the plane. You're right. Good. Yeah, because we saw two pivots means it's going to form a plane. And this is the equation of the plane. Yeah. In R3, this is the, or either one of those, this is the equation of that plane. Yeah, it's something that comes up sometimes in like, in multivariable, and we'll come to this class too, the idea of like parametrizing something. Like you could also describe this as a parametric description of the plane, because I have these two parameters, x1, x2, and I can pick those to be anything, and then it'll just like generate all the points in the plane. Versus this isn't really a parametric description. Although you could write down something like, I mean, it's kind of funny because you could write down like, once you pick like y3 is kind of, well, no, it's actually, there's two free variables, right? y2 and y3 are free, and then y1 would have to be y2 plus y3 over 2 or something. So you could give some sort of description like that. Okay. Okay, so that's that stuff I wanted to talk about, kind of the vector, just how you describe an image like as explicitly as possible. And then we've answered part C, like the matrix is that, and the span of the columns is the same thing as the image. I want to talk about part D briefly, and then part E I want to actually do because of this, like, this is going to be important because this is going to be what the definition of a linear transformation is. So let's do that. So the other thing, and this is going to come up later, is this idea that if you plug in the I vector, you're going to get the first column of the matrix, and if you plug in the J vector, you're going to get the second column of the matrix. That's actually kind of a cool, it's going to turn out to be useful. So notice T of I, which is really, I just really by that mean the vector 1, 0. Well, it's, I erased the matrix, but I guess it's up there. I can either just plug it into the formulas, or I could just say it's 1, 2, 0, 1, negative 1, 3 times 1, 0 like that. And actually, here's where it's useful to think of this as these as weights on the columns, because this is the same thing as 1 times the first column plus 0 times the second column. And this sort of shows you why you get the first column, right? So T of 1, 0 is the first column of A. Yeah. A. And similarly, T of 0, 1 is the second column of A. Maybe I'll tease why this is going to be important. So the next thing we're going to do starting Thursday, I think, is try to find the matrix for various geometric transformations. So like, I think I mentioned, like, if you want to rotate the entire plane like 90 degrees or reflect the plane or do some weird transformations, you can do that. It turns out you can often find a matrix representing that transformation. But then you might think writing down that matrix is hard, except if I just watch what happens to like these two vectors. If I just see geometrically what happens to this vector and what happens to this vector, then I can write down the first column of the matrix and the second column of the matrix. And I'm done. So you can actually write down transformations, geometric transformations that might seem complicated. You can write the matrix down pretty quickly because of this fact right here. All you need to know is where these two vectors go under the transformation, and that'll give you the matrix. Anyways, we'll see examples of that, but I'm just trying to like, we'll do that soon. But it's just a nice fact to remember that, like, yeah, the columns of the matrix sort of pop out of what happens to the standard basis vectors. Remember I called those. Okay. And T of 0 is 0, right? Also see the 0. If I plug in 0 and 0, I just get 0. That'll come up in a moment. So then there's this part E, which is this like the idea that the linear transformation sort of distributes over addition. Or a way a mathematician would say it is like it preserves addition. So consider, let's just do this for this example, because this is the kind of argument that comes up over and over again in this subject, and it's kind of worth seeing how it works. And then let's compute T of x plus u. So that's T of really x1 plus u1, x2 plus u2. Right, if I just add the two vectors together. And if I plug those in, I'll actually just use the actual transformation definition. Like, we can plug those in, right? The thing that the transformation says, the first row is we just add the two inputs together, two input numbers together. So that's like x1 plus u1 plus x2 plus u2, right? The second says do twice the first minus the second. So that's twice x1 plus u1 minus quantity x2 plus u2. And the third one says just 3 times the second input. So that's like that, right? You see what I'm doing there? I'm just plugging in. And then this is sort of nice because what you can do is you can just rearrange. It's a lot of distributive law, commutative law, just rearranging stuff, right? So I can put the x's together and I can put the u's together. So this is the same thing as x1 plus x2 plus quantity u1 plus u2. Let's just rearrange. This is 2x1 minus x2 quantity plus 2u1 minus u2. If I just rearrange the second row. And I can think of this as 3x2 plus 3u2. Like that, right? So I'm just rearranging the variables. And then you can break that up into two vectors. It seems like a lot of a lot of ridiculous like rearrangements and stuff. But the point is that you end up getting t of x plus t of u. If you just see it, all I did was like rearrange things. I saw some groups do it, and I know last time a few groups were writing stuff like this down on the boards. So yeah, I mean, really the way to say it is you can either add the vectors before or after you perform the linear transformation, and you get the same thing. So we could say something like, you could say t distributes over addition, or you could say t preserves addition. You know, it's that classic thing, right? Like, it's that classic mistake that students always want to make. You kind of want everything to preserve addition, to distribute over addition, right? When students first learn this, they want to write x squared plus y squared. They want the squaring to distribute over addition. But that's not, it's not linear. Like linearity is going to basically be this idea, and nonlinearity is going to be that idea, right? But it's an interesting thing that students want everything to distribute over addition. So it's like a natural property. Very similarly, if we do C times, so put that here. So similarly, T of Cx is T of C times x1, x2. That's T of Cx1, Cx2. Probably more steps than I needed to say that. And then we can plug that into the transformation. So we get Cx1 plus Cx2, 2 Cx1 minus Cx2, and 3 Cx2, right? Am I doing that right? I'm just plugging those in. But now we can just distribute all the C's out. We can distribute them out of each term, and then we can distribute it out of the whole vector. So that's the same thing as C times x1 plus x2, C times 2x1 minus x2, C times 3x2. That's C times all this stuff, if I just pull it all the way out, and that's C times T of X. So basically, again, I can either scale before or after I perform the transformation. And so this would be T preserves scaling. And it's not like, this might not seem like the most illuminating thing to do, but it really is the abstract definition of a linear transformation, is that it does these two things. And if you go to the handout and look, there's a definition down here, basically, where it's like, remember I say V and W instead of like Rn and Rm, but they satisfy these two properties that basically preserves addition and preserves scaling. Okay. And so yeah, these are really the definition of linear transformation. Okay. And yeah, I guess in that paragraph below, I talk about it preserving. They don't just fling points randomly about. In fact, let me just show number 6 because this actually comes up on the problem set. It's sort of a nice thing that like, anytime you write down like T of W, but W is in terms of some like, maybe like basis vectors or something, then you can write in terms of V1 and V2. So Yeah, let's see. So yeah, this is like the definition of linear transformation. Or like the defining property of linear transformations. Defining. It's that it's this T of V1 plus V2 equals T of V1 plus T of V2, and that T of CV is C times T of V. Right, those are the defining properties, I guess I should say. Properties. And in particular, there's a couple things you could say here. Like, for example, if you have T of C1 V1 plus C2 V2, you can actually just write that as, you know, you can pull the constants out and then distribute over addition. I guess the order would be the other way. You would distribute over addition and then pull the constants out, right? And for example, just as an example, like another way to say this is if we have something like x1, x2, although this is more general, this could be like in 27 dimensions, right? But if you have something like this, actually, maybe I'll do it with 3. If you have a transformation that takes in 3 numbers, I can actually write that as x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3 times 0, 0, 1. Right? There's no reason I can't rewrite that vector that way. And if you think about what this linearity says, it's that like that equals x1 times t of 1, 0, 0 plus x2 times t applied to 0, 1, 0 plus x3 times t applied to 0, 0, 1. So it's that thing I was saying that like once you know what happens to the standard basis vectors, then you can determine what happens to any vector. Right? So you just need to know what happens to 1, 0, 0, 0, 1, 0, 0, 0, 1 if your inputs are 3-dimensional, and then that kind of determines everything. Yeah. Okay, a little abstract, a little maybe boring, but kind of necessary. So what I was thinking we might do is do you guys want to do 4 in groups or do you just want to skip it? Something similar to what we just did. Maybe we'll skip it. I think it's interesting to see how things fail to be nonlinear, fail to be linear. Oh, sorry, one last thing I wanted to say. By the way, it turns out that for all linear transformations, that if you plug in if you input the 0 vector, you get out the 0 vector. So note. Here's a nice argument. I can actually rewrite the 0 vector as the 0 vector plus the 0 vector. It's kind of silly, but there's no reason you can't do that. And then I could distribute over addition, right? And I guess I could do something like this. Say T of 0 is V. Then what this says is that we just showed that V equals V plus V. And what's the only vector for which that's true? The 0 vector, right? Yeah. And that implies V equals 0. So it's always true in a linear transformation that the zero, that t of 0 equals 0. That's kind of an argument. It's kind of like a proof that like you could always sort of justify that t of 0. If you have a linear transformation, t of 0 has to be 0. Okay. Okay, so I think what would be instructive would be to do number 5 to see how some things are not linear. And then number 7 is kind of fun, although you'll probably need a device or something, or you'll have to draw on the board. We did number 6, but number 7 is like actually kind of illustrating linearity, or like by drawing some vectors on these pictures. Like you would draw V and W here, and then you would draw T of V and T of W there. And something similar to illustrate. And it's for this specific transformation right here. Okay, and then the next page is kind of abstract, but there is an interesting thing if you finish those to go on to 13, because there's actually, it turns out you can multiply matrices in certain cases. And it turns out it has a lot to do with function composition. And you can sort of derive the definition of matrix multiplication from, if you sort of work through some of these examples, you can sort of figure out how matrix multiplication should work, which I think is kind of neat. So yeah, let's do 5, 7. Let me write this on the board. So group work. 5, 7, and then 13 on. (13) through whatever, however far you get. Okay, that sound like a plan. Can we do group work? Let's do it. Group work. So go back, pull up the handout, go back to number 5. You guys can go to the boards. Same groups, I guess, since you were working on these already. Try working through number 5. Then number 7 is like drawing. And then 13 and on is kind of fun. Eyes. And I'll erase this board for you. I should pause the recording also. Fell asleep 8 times in class, is that what you said?
No. I was planning to wake up at 7:30.
Oh, you snoozed 8
And
times?
I got out of bed at 8.
I always snooze a few times. I set like 4 different alarms, so I don't sleep through.
In the end, I'm like, oh, I might just go back to sleep for like 30 minutes.
All right, let me pause the recording.